Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on XRD and XRR. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Ian McDonald, scientist at EAG Laboratories.
Thank you, Rena. I'd like to welcome everyone to the second installment of our Smart Chart webinar series. This week, we'll be covering two X-ray based techniques, X-ray diffraction and X-ray reflectivity. My name is Ian McDonald. I am a scientist at EAG's laboratory in Sunnyvale, California. My career thus far has focused heavily on materials characterization through many diverse techniques, but my primary focus at EAG and what I'll be speaking about today is X-ray diffraction and X-ray reflectivity. I'll begin this webinar with an introduction to EAG, followed by a closer look at our Smart Chart reference material. After that, I'll dive into XRD with a brief overview of its uses, a high-level look at the fundamental concepts behind the technique, and I'll finish with a few practical examples to show off what it can do. Then I'll repeat this structure for X-ray reflectivity as well. EAG has several hundred highly educated employees working in laboratories around the world. However, we only offer XRD and XRR in two locations, here in California and our recent addition in the Netherlands. Our range of equipment and diversity of expertise allows us to provide our clients with a comprehensive peer-reviewed report within a few days of sample receipt. When necessary, we can even provide same-day service. EAG services a broad swath of industries across the globe, from pharmaceuticals to aerospace, medical devices, to semiconductor manufacturers located right here in our backyard. I should also note that we do have an organization-wide quality system, either ISO 17025 or 9001 for many techniques, and are both ITAR registered and DEA certified. We test instrument performance weekly and have external audits by both accreditation bodies and clients. Here at our Sunnyvale location, we have 6 highly trained professionals who are all experts in X-ray diffraction and X-ray reflectivity. In fact, combined, we have over 100 years of experience that we utilize on a daily basis to deliver accurate, reliable answers to any problems you may have. Believe me, we have seen it all. In this lab, we've collected a near army of specialized instruments to handle whatever gets thrown our way. While others may be satisfied with a Swiss Army knife approach, using just 1 or 2 general use instruments, we believe that having instruments that are optimized for each type of work allows us to deliver quicker, more reliable results to our clients. Currently, despite the shutdown to many industries, our turnaround time remains between 3 and 5 days. For instance, we've got 2 instruments configured specifically to run wafer and thin film samples. Each of these instruments can accommodate anything from a small coupon to a full 300 millimeter wafer. Here in the front on the right, this is one of our Rigaku Smart Lab instruments that we can configure to run our high temperature stage. This stage is able to heat samples up to approximately 1400 degrees Celsius under a variety of atmospheres and is perfect for tracking the change in your sample's phase makeup, grain size, or stress relaxation with temperature. And finally, I'll point out our newest instrument on the left. This is one we just recently acquired and is optimized to run pharmaceutical samples or medical devices. It's got a low temperature stage that can reach down to -180 C, all under vacuum or a variety of atmospheres, as well as controlled humidity. Hopefully this brief tour gives you an idea of the immense capabilities we have available to us. Here we have our smart chart. This is what we call our spectroscopy and microscopy analysis resolution tool, or smart chart. Each of the bubbles represents a different analysis technique. On the y-axis is detection range, going from macro to parts per million, and the x-axis is analytical spot size, going from macroscopic to sub-nanometer. Inside the box, you'll find surface analysis techniques. Outside the box, on the right, we have bulk techniques. These techniques have a range of detection limits for composition, but do not provide information regarding depth. Below the box are the imaging techniques. These can measure surface properties and features of various sizes, but they do not provide information on chemical composition. The last feature is color. The bubbles are color-coded to indicate the type of information each technique provides. Looking inside the box of surface analysis techniques, the blue bubbles show techniques that provide elemental information. The orange bubbles, such as XRD, provide molecular bonding and oxidation state, or structural information. First up, for today, we are looking at XRD. XRD is located inside the box, indicating that it is a surface analysis technique. However, it should be noted that the penetration depth will depend on a number of key factors. You'll also notice the colors. XRD is orange, as it provides mainly bonding or structural information. If you remember nothing else about XRD today, remember that X-ray diffraction is used to study the structure of materials. XRD is a very powerful tool that can provide a wide variety of information. Here we have a few of the most common applications, but this list is by no means exhaustive. They include identification of unknown samples, confirmation of material phases within those samples, a quantification of phase ratio of those material phases. We can even detect trace contamination. We can measure residual stress in wafers or thin films and the crystallinity of coatings. We can even compare subsurface damage or defect density in thin film samples or measure wafer offcut. Lattice mismatch is something else that we also can cover. XRD is also a very versatile tool that can provide information about nearly any kind of sample you can think of, provided that it's solid. Any geometry from powders to thin films, any type of material from polymers to ceramics, and some totally off-the-wall samples. And yes, we have tested cheese before. Here at EAG, we can accommodate almost any size of sample too, from a single microscopic particle to a 300 millimeter wafer. Distinct from the actual sample size, however, is sampling area. We have instruments capable of measuring a spot size of roughly 2 by 2 centimeters, all the way down to about 20 microns. We also have ways of tailoring the penetration depth to some degree that allows us to target specific regions and layers within a sample. A few of the major benefits of XRD are that it is entirely non-destructive and can be performed in an ambient environment with minimal sample prep. However, if the sample demands it, we do have the capability to run our measurements at low or high temperatures in a non-ambient environment or with a controlled humidity. Just ask and we'd be more than happy to figure it out for you. Now let's dive into a bit of the fundamentals behind XRD. I'm going to give a high-level explanation of how this technique operates, but I'd be more than happy to go into further details with anyone who's curious. The number one thing to know about XRD is that it probes crystal structure, or atomic arrangement. A given sample may have the same exact composition, but will have very different properties if the atoms are arranged differently, as illustrated in this graphic here. These are two polymorphs of aluminum oxide, cubic on the left and trigonal on the right. Both are aluminum oxide with the same composition, but they have very different crystal structures, and thus they have very different material properties. This is the type of distinction in structure that XRD really excels at. Speaking of structure, XRD won't be able to do much if the material has no structure to begin with. XRD provides primarily information about crystalline materials. Crystalline just means that there is some long-range order. Take this example on the bottom. The bricks are lined up neatly, one after the other. There is some repeating pattern that continues indefinitely. This is analogous to a single crystal material. Next to it is a brick walkway with a very nice pattern, but these bricks are lined up in some repeating order that doesn't continue indefinitely. There are regions that are oriented in different directions, but the bricks are all laid out nicely in some ordered fashion. This is analogous to a polycrystalline material in that there are discrete areas with the same order, but there are different orientations. Finally, with a pile of bricks, there's no order. Just like the bricks, an amorphous material has no long-range order. And while XRD can provide some information on amorphous materials, it is largely used to study crystalline materials. And how does it study those materials? Well, as we saw on the last slide, crystalline materials are made of atoms arranged in certain ordered configurations with specific spacings. XRD reads this information like a fingerprint. X-rays are scattered off planes of atoms, and the interference of those scattered X-rays produces a pattern that provides a wealth of information about the atomic structure. In a typical theta to theta measurement, the angle of the incoming X-rays relative to the surface is the same as the outgoing X-rays. However, in some instances, we just want to look at the top portion of a sample. In this case, we can use a technique called grazing incidence X-ray diffraction. In this case, the incident X-rays are fixed at a very shallow angle, typically under 1 degree, while the angle of the detector is still varied. This allows us to restrict the penetration depth and generate more of a surface-sensitive measurement. And now, here is a typical fingerprint or XRD spectra with diffracted intensity as a function of angle. By interpreting the key features of this spectra, we can conclude a great deal of information about what the sample is made of. Some key features you'll notice are diffraction peak position, peak shape, and the area under each peak. Now let's put it all together. I'll give a few of the more common analysis techniques and show just how much information we can pull out of a single measurement. Here we have a complex diffraction pattern with a number of very interesting features. First, we have a background that is slightly higher at low angles. This raised background originates from air scatter along the beam path that is more prevalent at lower incident angles. We have a number of diffraction peaks, some more narrow and some more broad. While the sharper peaks on the right are coming from crystalline materials, there's also a broad band located towards the left of the plot that represents an amorphous component of the sample. Using the ratio of peak areas from the sharp peaks versus that of the broad peaks, we can estimate just how much of the sample is crystalline and how much is amorphous. As an example, this type of analysis may be used to determine whether, say, a coating deposited on a representative substrate is amorphous or if it has crystallized due to annealing. Next, by examining the positions of each of the sharp diffraction peaks and referring to a database of reference materials, we can determine the different phases that this sample is made of. In this case, we've got both titanium nitride and corundum. We can then model this diffraction pattern to acquire quantification of the phases in this sample. This type of measurement is the most common and can be used to identify contaminants in powder materials or distinguish between polymorphs. Next, we take a closer look at the width of these diffraction peaks. By examining how broad or how narrow a diffraction peak is, we can determine the average grain size of that particular phase. This technique may be used for studying differences in grain size due to growth or solidification processes. It can even tell if you have equiaxed grains or if they are more elongated. Next up is texture or preferred orientation. This information is contained in the ratios of the diffraction peaks and their intensities, and how they compare to our reference materials. This type of analysis is often used for determining preferred orientation in thin film samples. Finally, we have residual stress. This is also a technique commonly used for thin film samples or coatings in which there may be some strain due to lattice mismatch or differences in thermal expansion coefficients. These are just a few of the more common uses for XRD, but you can see how much information you can pull out of a single measurement. I do want to just touch briefly, though, on some of the more advanced techniques that we have the capability of here at EIG. With such a wide array of tools at our hands, we have the flexibility and equipment to swap in some high-resolution optics and run measurements, such as determining texture, far more precisely from rocking curves or even pole figures, instead of the typical peak ratio method. Our measuring those high-res rocking curves in 4 orthogonal directions can allow us to determine wafer offcut as well. Or we can even record the lattice mismatch of an epitaxial grown thin film. All of this and more is possible with all the advanced equipment that we have here. All right, next I'd like to run through a few practical examples of the types of problems we can encounter here at EIG and how we go about solving them. Hopefully these 4 examples will give you a little bit of a look into the capabilities we have at our disposal. For the first example, we have the history of a penny. The American penny, the smallest denomination in circulation. In fact, some people want to get rid of it altogether as they don't see it serving much of a purpose. Well, we wanted to take a look into the history of this controversial coin and compare 2 pennies from very different eras, one from 1973 and the other from 2002. Surprisingly, the newer coin was much dirtier. We're going to use XRD to compare what these 2 pennies are made of, how they're similar and how they're different. Then, as an added bonus, we noticed that there was a small spot of discoloration under the newer penny, and we wanted to investigate that just a little bit more. We ran a typical theta 2 theta measurement on both pennies to gather information about what they were made of. The older penny showed diffraction peaks that matched fairly well with copper. Not too surprising, but we noticed that the peaks didn't quite line up with those of pure copper. This suggests the copper is alloyed with another metal and has a slightly altered lattice parameter. You can see the plot here on the top right. We turned to X-ray fluorescence, a complementary technique that provides elemental information. XRF was then able to determine that the composition of the 1973 penny was largely copper, but it did contain a few % of zinc. So let's move on to the next penny, the one from 2002. Running the same XRD measurement on this penny resulted in a very different spectra, one that matched up with the hexagonal zinc structure. You can see the structure, you can see the XRD pattern on the bottom right here. However, so there were a few extra peaks in addition to the hexagonal zinc. These peaks matched up to cubic copper, and XRF was able to confirm the presence of both zinc and copper in this penny, but they were in a very different ratio than the first penny. We can see these results tell us that while the older penny consisted of a copper alloy with some zinc in there, the newer penny contains both zinc and copper separate from one another because we have diffraction patterns that are discrete from one another. This is actually interesting because this is what the case is. Before 1982, pennies were made of an alloy that was mostly copper, but did contain some amount of zinc. However, as the value of American currency changed, the US government decided to save money while making it, so they switched to a penny that was made of zinc but plated on the outside in copper. The X-rays will penetrate through the copper plating into the zinc that makes up the bulk of the penny, so we get signal from both. In today's money, that 1973 penny would be worth almost triple what it originally was, which, still isn't a whole lot. Next up, we wanted to take a look at that little bit of discoloration. For this, we wanted to use our microdiffraction system. Microdiffraction focuses the X-ray beam onto a very small spot. With our system, we can get down to somewhere around 25 microns under ideal conditions. Then, because we're only analyzing a very small area, we have an extra large area detector that catches a much wider portion of the X-rays diffracted from that spot. For this study, we used the microdiffraction system to zoom in on a small discoloration and target just that rather than the entire penny. You can see this discoloration right here beneath Lincoln's nose. What we found actually wasn't all that surprising. This discoloration was a bit of cuprate, a very common form of copper oxide. A snippet of that diffraction pattern is shown there on the left. This technique is incredibly useful and can be used in a number of applications, from targeting a specific area on an integrated circuit to pinpointing a single particle that doesn't quite look like the rest. In our next example, I'll demonstrate a bit about our high temperature capabilities. Here we're looking at lead titanate. Lead titanate is a common material for many modern sensing and memory applications, particularly those that make use of ferroelectric sensors, such as ultrasound machines, sonar, RFID chips. That's because lead titanate is ferroelectric below a certain transition temperature. Ferroelectricity is simply a characteristic that gives materials a spontaneous electric polarization that can be easily reversed with an electric field. You can think of it as a little switch, either up or down. The figure here shows lead titanate in its low temperature form, which has a tetragonal crystal structure. The displacement of that central titanium cation determines the direction of the electric polarization. You can see why it's so useful in computer memory. This electric dipole can function as either a 0 or a 1 depending on its position. However, if we heat this material above a certain temperature, there is a structural phase transformation from the tetragonal crystal structure on the left to a cubic one on the right, and it loses all of its ferroelectricity. The objective of this study was to monitor the crystal structure through that phase transformation and to get an estimate of the transition temperature. We start with a room temperature measurement of the lead titanate sample. You can clearly see the diffraction peaks match up with the reference pattern for the tetragonal lead titanate. You'll notice the splitting or doubling of many intense diffraction peaks. This splitting is caused by a lowering of symmetry due to the differences between the height and width of the unit cell. Okay, now let's heat things up. We increased the temperature of the sample in our high temperature sample stage while under vacuum, stopping to collect a full spectra at roughly 50-degree increments. Here you can see the diffraction pattern changes with an increase in temperature. Some of those split diffraction peaks begin to come together as the symmetry of the unit cell increases with the transition to the cubic form. While this way of looking at it is very eye-catching, maybe we can put it in a form that's a little easier to see what's going on. This is a little better and a little bit easier to read. This plot is showing peak locations in 2 theta as the temperature is increased. Each horizontal slice is its own diffraction pattern, compressed down to something a little more manageable. We can see that the tetragonal splitting begins to go away right about 500 degrees Celsius. And in fact, if we plot the change in lattice parameter, we see the transition occurring right around there. While this transition temperature is listed as a bit under 500 C in the literature, it should be noted that this transformation is classified as a second order transition, meaning it occurs in a continuous manner over a range of temperatures rather than happening abruptly. That being said, next steps for this study may be to narrow the scan range so that measurements don't take quite so long and to ensure the sample reaches thermal equilibrium at each point. This next example deals with a very interesting material called yttria stabilized zirconia. While this material is a common refractory material used for its thermal properties, it's also widely used across a number of industries thanks to its very high hardness and good wear resistance. It finds application in everything from dental crowns to gas turbines, and it's even what they use to make those ceramic knives that you see on infomercials. Pro tip, those knives aren't actually worth it because they chip rather than dull, and you can't resharpen them like regular knives. This particular case study was looking at some failed refractory material made of yttria stabilized zirconia, or YSZ. We have one good sample and one bad sample. Let's take a look at each of these using XRD techniques that we have at our disposal. First, we have the good sample. We ran a typical theta 2 theta measurement that would probe the bulk of the sample, then matched the diffraction pattern to our reference database and found a match to the cubic form of YSZ. With no indication of any additional phases, this sample did seem to be good. Now let's examine the bad sample. Here it becomes clear what the problem is. After running the same measurement on the bad sample, we find that the diffraction pattern is quite a bit more complex. We were able to find clear evidence of 3 distinct material phases, the cubic, tetragonal, and monoclinic phases of YSZ. Then, by modeling the data using our whole pattern fitting method, we quantified how much of each phase was contained in this sample. While the good sample was made entirely of the cubic phase of YSZ, this sample only contained about 25% of the cubic phase. This is a key point since phase composition makes such a huge difference for this material. Let me explain why that's so important. While the elemental compositions of some of these phases may not significantly be different, there are some major discrepancies in other material properties. Besides the fact that the phase transformation from one to another involves unit cell volume changes that can introduce stresses to the sample, the coefficient of thermal expansion is also very different between each phase. This could produce even more of a buildup of stress during thermal cycling. Finally, the monoclinic phase of YSZ is especially susceptible to corrosion in the presence of water and could have definitely contributed to this piece failing if there was moisture around. As you can see from the illustration at the bottom, the transformation from the cubic phase to the monoclinic phase contributes to the propagation of cracks formed through corrosion. The difference between having trace amounts of the monoclinic phase and having more than 20% is a difference between a good sample and a bad one. Our final example is probably the most interesting of the bunch. In this example, I'll be walking through an effort of ours to spot counterfeit jewelry made of jade. Jade is a popular gemstone used in many types of jewelry and artwork worldwide. This gem is comprised of one of 2 minerals, either jadeite or nephrite. Often jade is sought out because historically it has been used to create hand-carved, culturally significant artifacts and art pieces that are, if not priceless, very expensive. These artifacts most often come from Asia or Mesoamerica. However, because these pieces are so highly regarded and valuable, there are, of course, counterfeiters. Fake jade is a huge industry that has always been lucrative, but is even more so in recent times. Now, counterfeit jade can be produced in a number of ways, but the most common is by using either cheaper minerals or enhancing the gem through a staining or resin impregnation process. The resin or epoxy fills in any pits there may be and hides imperfections. Untreated jade, however, is very rare and expensive. As it turns out, one of our own XRD scientists happened to own 3 pieces of jade jewelry, a necklace, 2 figurines, a bear, and a rabbit. So we decided to test these 3 pieces to see if he spent his money well. XRD should be able to determine the phase composition of the stones, whether or not they're made of jadeite or nephrite, but we will need to use another technique to determine whether the stone has been treated. First up, we looked at the small bear figurine, and pretty quickly we found that this piece was made entirely of quartz, likely stained green to give the appearance of jade. I hope my coworker didn't pay too much for this one. It's not looking great. So far, 0 for 1. Next, we looked at the necklace. Here we have a somewhat more complicated XRD pattern. However, we can see that the spectrum matches very well to actinolite, which is the umbrella term for minerals that include nephrite. So thus far, this one appears to be real. We'll see. Last is the little rabbit figurine. Now this one is big enough to run on any other machine like the others, but due to the curved surfaces, we chose to use the micro diffractometer with a 2D area detector. Looking at this plot of diffracted intensity versus angle, we can quite easily match it up to the reference pattern for jadeite, another potential real jade piece. Okay, they're looking good. Now let's move on to the second check and see what we find. A complementary technique, Fourier transformed infrared spectroscopy, or FTIR, was used to check for resin impregnation. FTIR exposes a sample to infrared light and can provide information about the chemical bonding based on what wavelengths of light are absorbed. We're using it here because resins and epoxies are amorphous and would only make up a small fraction of the total volume of these samples, meaning it's basically invisible to XRD. But FTIR works great for organic compounds and should be able to fill in for the limitations of XRD. First up is the bear. Well, we already know the bear is made of cheap quartz, so this one is definitely fake. It's just quartz and it's been dyed green to look like jade. Next is the necklace. Now XRD found that this was made of nephrite, one of the 2 jade minerals, so there's hope that this could be real. But FTIR found, unfortunately, that the necklace is made of nephrite, but it has been treated with epoxy to fill in pits and cover up imperfections. This one is deemed to have been enhanced or treated and is not real jade. Tough luck on that one, that was close. Finally, we have the little rabbit figurine. Well, to all of our surprise, this rabbit actually turned out to be real jade. It was made of jadeite and it showed no signs of being enhanced with epoxy. So it looks like our guy got a pretty good deal on this one. Finally, for this section, I want to summarize what I've discussed of XRD by giving a brief snapshot of the key strengths and limitations of this technique. First, XRD can analyze almost any solid sample. We can gather qualitative or quantitative phase information about the material, the phases in that material. We can accommodate a wide range of sample sizes and thicknesses, and all of our tests are non-destructive with minimal sample prep. But we do have the capability to do both low and high temperature measurements, as well as controlling atmosphere and humidity. Some of the limitations include the fact that we can't measure liquid samples, but that makes sense because we would need to be looking for a structure. We can identify amorphous materials, but we can't identify them compositionally, only tell you that we have some amorphous material in there. Finally, our detection limit can be a bit of a disadvantage, but there are some ways around this. Next up, we'll be talking about X-ray reflectivity. Here's our trusty smart chart once again. If you'll remember, the techniques inside the box are all surface analysis techniques. XRR is also colored blue, indicating that it will provide compositional information. If you remember nothing else about XRR, remember that X-ray reflectivity accurately measures the density, thickness, and roughness of thin films. XRR is a powerful tool that can provide critical information on thin film samples. Here we have a few of the most common applications, but again, this list is by no means exhaustive. We can qualify thin film growth conditions by determining film thicknesses and doing depth depth profiling of film densities. We can investigate interfacial roughness or intermixing between layers and measure film uniformity across a wafer. XRR is a more specialized technique than XRD and is primarily limited to the study of thin film samples. Moreover, the sample surface must be relatively smooth to avoid scattering from the top surface. A good rule of thumb is that you should be able to see yourself in the sample just like a mirror. If not, then it's likely not smooth enough for XRR. As I'll explain in just a slide or two, XRR makes use of a very shallow incident angle. Unfortunately, this spreads out the analytical spot size a great deal, meaning that the area that is being probed will be on the order of a centimeter or two squared. While XRR is possible on smaller samples, for better results, a bigger sample is always better. As mentioned already, XRR is used to determine the layer thickness, density, and roughness of thin film samples. The ideal range of thicknesses is somewhere between 2 nanometers and 300 nanometers. Below a few nanometers, roughness on the same order as the layer thickness becomes an issue, and the film layer can become non-continuous. Above 300 nanometers, the instrument resolution becomes a problem, and while we can still extract some information, such as surface roughness and density, this technique won't be able to tell you anything about the thickness of that film. At thicknesses like this, we would hand it off to our optical profilometry experts down the hall, and just like with XRD, this technique is non-destructive, runs in an ambient environment, and requires essentially no sample prep. Now on to a little about how XRR works. If you'll remember my previous slide on XRD, this may look familiar. While XRD uses interference from X-rays scattered from atomic planes, XRR utilizes the same principle, but the X-rays are scattered from the interfaces between film layers. Using very small diffraction angles, variation in the electron density profiles at interfaces between layers in a thin film sample create a pattern of interference fringes. We can then use a powerful simulation tool to accurately reproduce and match the reflectivity pattern to calculate the thickness and density of each film layer, as well as the interfacial roughness between each layer. A key feature that sets us apart from XRD is that the film can be amorphous or crystalline, and no prior knowledge or assumptions regarding the optical properties of the films are required, unlike something like optical ellipsometry. Here I'll briefly break down the type of data we obtain from an XRR measurement. The incident angle between an incoming beam of monochromatic, non-divergent X-rays and the sample surface begins at nearly zero. At this point, the X-rays are being completely reflected from the surface of the sample, as if it were a mirror. As the angle of incidence is increased, the X-rays begin to penetrate into the sample at a key angle named the critical angle. The critical angle is solely a function of the density at the top 30 to 40 nanometers of the sample. As the X-rays penetrate the sample, they are reflected from buried interfaces, and their interference with one another produces a pattern of interference fringes. The periodicity of these fringes depends upon the layer thicknesses and the slope, or how quickly the intensity decays as a function of the roughness of the surface that the X-rays encounter. To illustrate this, I've simulated a 50 nanometer layer of aluminum oxide on a silicon substrate. I've kept all parameters constant except for the density of the aluminum oxide, which I vary between 3.2 and 4. Consider it like an experiment to determine the effective deposition temperature on the density of the film, say. In the plot on the right, you'll see intensity as a function of angle, with the angle being very small because it is X-ray reflectivity. You'll notice that with an increase in Al2O3 density, the XRR pattern will shift to the right. With a higher density, the angle of X-rays must be more severe before they begin to penetrate into the sample, pushing the critical angle towards a higher angle. Next, I took that aluminum oxide film, kept the density constant at 4 grams per cc, and vary the thickness from 20 nanometers in blue to 50 in red, and finally 100 in green. From this, you can clearly see that the broadness of these interference fringes are inversely proportional to the thickness of the film layer. The thicker the film, the narrower and closer together the fringes are, until they become smaller than the resolution of the instrument. At that point, no fringes can be resolved, only the density and roughness can be calculated. And finally, with a sapphire film with the same density and a thickness of 100 nanometers, I varied the roughness of the top aluminum oxide surface from 1 in blue, 2 in red, and 5 in green. So with a roughness of 5 nanometers, that's pretty significant. With an increase in roughness, the XRR signal is dampened at higher incident angles. A more rough interface or surface will diffusely scatter the X-rays and dampen the reflectivity signal. All right, let's move on to something a bit more complex. Here I've got an example here that will hopefully illustrate the power of this technique and our capabilities at EAG. Here I've got an example of the type of sample that a client might send us. It's a multi-stack thin film sample with thermal oxide grown on a silicon substrate. Then an underlayer of titanium nitride was deposited using physical vapor deposition, and finally topped with a thin layer of tungsten. The client in this case wants to know the grain size of the tungsten layer and have a confirmation of the tungsten layer thickness. So now a typical XRD measurement in a theta to theta configuration would probably penetrate far too deep into the sample, and we'd be getting our signal mostly from the silicon substrate and the amorphous oxide. So instead, we employed a technique, which I mentioned earlier, grazing incidence XRD, where the incident angle is set to a very shallow angle, so as to restrict the penetration depth of the X-rays. This technique highlights only the topmost layers and reveals our tungsten diffraction peaks. From this, we were able to resolve crystallite size for both the tungsten film and the titanium nitride. So now that we've determined the average grain size for the top layers, we need to find out the tungsten layer thickness. While XRD cannot accurately distinguish between two amorphous layers and has difficulty with overlapping peaks from nanocrystalline materials, XRR can do this very easily provided there's a difference in density. So we can see here from the XRR model that we have two distinct layers that, while amorphous or close to amorphous, can be separated based on the difference in densities. The thickness of the tungsten layer here can be easily resolved, and we can see the numbers in the table on the top right. Now, if we wanted to take this one step further, we can turn to our friends over in XRF to map the layer thicknesses for the entire wafer. While the thickness is determined via XRR as a calibration, XRF can then provide a thickness map for the whole wafer. And in this way, we can use one XRR measurement and then a much quicker XRF measurement to measure the thickness of different layers in a full wafer. Finally, for this section, I want to summarize what I've discussed regarding X-ray reflectivity by giving you a brief snapshot of the key strengths and limitations of this technique. Some of the key strengths are that it can resolve absolute layer thickness and density with no standards needed. It can analyze multi-layer film stacks non-destructively and has no problem measuring amorphous films. And unlike ellipsometry, there's no need to know the optical properties or any properties beforehand, although it does help. Some of the limitations, though, is that it cannot tell composition information per se, but only density of the films. Similarly, if two film layers have similar densities, there may be some issue in resolving differences between those two. And the analytical area tends to be kind of large. So again, in this case, it's better to send a larger sample. Like you saw in many of these examples, EAG has a wide variety and collection of diverse techniques at our fingertips, and often literally just down the hall. No problem is too big for us. We'll continue the Smart Chart webinar series over the next several weeks to explore more of these techniques in depth. And I'd be remiss if I didn't plug the company just a little bit more. Here at EAG, client confidentiality is key to our day-to-day business. We have endless experience and a broad range of techniques and expertise in very different disciplines. Using this expertise, we can meet your needs in a timely manner with accurate and reliable results with a number of instruments worldwide. We can help to solve your materials and engineering related product problems. All right, thank you all for tuning in today. I'd like to remind you that EAG will be continuing this seminar series in the coming weeks with seminars covering atomic force microscopy, as well as more X-ray techniques like XRF, the one I mentioned earlier, organic analysis, Rutherford backscattering, nanoindentation, and much, much more. Thank you again, stay safe and stay healthy.